Hey everybody, welcome back. I hope you're having a good day. And rather than start the aromaticity and reactions of aromatics chapter today, I thought it really couldn't hurt for us to do 2 or 3 videos just reviewing a lot of what we've already gone through. So the general gist of everything we've been doing in this chapter, and it is a great big chapter and I understand that, involves aldol. Wow, I messed up already. Involves enolates and enols. And then ultimately, these two really got lumped together into the same basic theme because that's how they work. Then finally, the last one we want to talk about over here is the addition to alpha, beta, unsaturated carbonyls. Now, the enols and the enolates, let's start with that first. The reactions that we looked at for those were principally this. 1, halogenation. We're going to revisit this in just a couple minutes. 2, alkylation. And then we get into aldol, both addition and condensation. For esters and amides. And then finally, the conjugate addition. The conjugate addition mostly occurs when you are working with aldol or esters and amides in the same sort of situation, condensations, because these are the times that you form a pi bond or a carbon-carbon pi bond that is in conjugation with your carbonyl. Now, since we kind of started here, let's look at halogenation of carbonyls. And there are 2 pathways through which this can occur. The electrophilic or acid pathway, or the nucleophilic or base pathway. So what we're going to do is we're going to look at the bromination of, I like acetaldehyde. We're going to start with this because it's simple. The reason acetaldehyde is simple is you have one site for enol or enolate chemistry. I'm still seeing a lot of people doing stuff that makes me angry. And one of those things that people are doing, and I don't think you're doing it just to honk me off, but it's a common misconception I want to break you of, is this proton. This proton is not acidic. And outside of the Canzonero reaction, which was the bonus on your last assignment that I graded, this is pretty much non-reactive. The proton is just kind of there, the hydrogen there. It's not a labile proton. All right, so using acetaldehyde, why don't we go ahead and show the different products we make through the acid and the electrophilic pathway. So we'll start here. Let's do the acid pathway first. So with the acid, what we've got is HBr and Br2. Now, a lot of you are going to be flipping out right now because I haven't told you it was HBr before. I just said hydronium. And that's right. HBr is the main acid you want to use here because the bromines match. If you use HCl or HI, then you might get some weirdness with the halogenations. So the HBr here, this is our acid source. And then the Br2 is the source of our halogen. Now, because I like to give you the punchline before I give you the joke, here is what the product of this would look like. Looks just like that. So, before we go into the mechanism, let's make a couple of notes here. Acid halogenation is an enol process, not enolate, because you've got too many spare protons running around here for that to be any kind of base that could form. So this is an enol, and it will brominate once. It will only brominate once, and then it will stop. So let's look at this mechanistically. So there is our enol. There's our aldehyde. Here's the hydronium. It is very difficult to get HBr away from water because they're so soluble. That's why we still use the hydronium here as our acid source. So, like with all enols, the carbonyl carbon snags the proton off of the water in a reversible step that looks like this. All right, this is halfway to our enol. The other half comes off like this. The water grabs that proton, forms the carbon-carbon pi bond, and breaks open the carbon-oxygen pi bond, which leads us, still in a reversible step, to here. Now, hopefully, some of you are noting by now that enols typically don't live very long. And I can't argue with that. They really don't. 99.99% of this enol will tautomerize back to the original aldehyde. But for the times it doesn't, here's how the addition works. This operates under a similar idea to the bromination of an alkene in that you have a high electron source here scaring the electrons away from the bromine. So you end up with an induced dipole that looks like this. Partially positive on the bromine, partially negative on the far bromine. And now we reform the carbon-oxygen pi bond. This pi bond attacks the electropositive bromine, cleaving the bromine-bromine bond. So we are here. And now all we need to do is remove that proton. I would probably use, I'm out of room so I can't show it. I would probably use water to pull that proton off of the oxygen. And then this is your product. Acid pathway, it stops at this point. Okay. What about the base or nucleophile pathway? Well, let's talk about that. Base or nucleophile bromination. The acid pathway is easy. This one is a little bit tougher. And you know what? We're not going to use that. We are going to use propano. That ketone. Now, why did I pick this ketone? Easy. This side, the aromatic ring, No protons to remove. See how I kind of biased the situation there? All right. So let's set this reaction up. Excess NaOH and excess Br2. This will be your product. You will get geminal dibromination. Okay, so this will fully halogenate the alpha carbon. Again, it doesn't happen with the benzene ring because there are no protons to pull off there in the first place. Now, I'm already at 11 minutes and I'm running out of time, so I'm going to go through this a little bit quicker than I probably would have otherwise. If you have any questions, as always, feel free to email me. Say something in the chat if you want to. I'm cool. All right, base deprotonates that hydrogen, and we form our enolate. That is actually a terrible drawing of an enolate there. Let's try that again. There we go. The enolate reforms the carbon-oxygen pi bond, attacks the bromine, knocks the bromine off, and what we get is this. Now, the difference between the acid pathway and the base or nucleophile pathway is that proton, this one right here, is still strong enough that it can be deprotonated by another base and put you here. Oh, whoops, my bad. Damn it. Like so. Reform the pi bond, attack the bromine, knock it off, and you get that. All right. I'm out of time on this video, so what I'm going to do is stop here, and when we come back, we'll talk about the bromoform reaction. So, everybody, have a good day.